All right, so let's go through some examples of balancing chemical equations. So if I take propane gas, C3H8, and I react it with oxygen gas, basically I'm burning the propane, I'm going to form CO2 and water. So I want to balance this equation. So keep in mind those rules. So the first thing I want to do is I want to start from the left and move towards the right. What that means is if I start at the very far left, I'm starting with that carbon in the C3H8. So I'm going to balance that carbon first. Well, how many carbons do I have on the reactant side? I have 3 of them. How many carbons do I have on the product side? I have 1 of them. So I need 2 more carbons on the product side. Now I can't simply just add carbons because that carbon is in a CO2 molecule. It's bonded to oxygens. So what I need to do is I actually need to add the actual CO2s so that I get 3 carbons. So if I have 3 CO2 molecules, I have 3 carbons there. And you notice I wrote those underneath. This is my way of keeping track of the number of atoms. This gives you something visually to look at. Do this. It's going to help you keep track of things. Okay, so now I have 3 carbons on the reactant side, 3 carbons on the product side. My carbons are balanced. I keep moving from left to right. I hit hydrogen now in the C3H8. Well, remember hint number 2, skip hydrogen and oxygen if at all possible. Well, if I skip the hydrogen, I end up with an oxygen, so all I have left is hydrogens and oxygens, so I'm not going to skip them. So I'm going to go back to this hydrogen. I've got 8 hydrogens on the reactant side. I've got 2 hydrogens on the product side. Those aren't equal. I need more hydrogens on the product side. Once again, though, I can't just add hydrogens because they're bonded to that oxygen in the water molecule. But what I can do is add additional water molecules. So if I add enough water molecules to get a sufficient number of hydrogens, I now have 8 hydrogens on the reactant side, 8 hydrogens on the product side. My hydrogens are balanced. So carbons are balanced, hydrogens are balanced. Now I'm going to move to my oxygen. I have 2 oxygens on my reactant side, and I have 10 oxygens total on my product side. How do I get 10 oxygens on my reactant side to equal the 10 oxygens on my product side? Well, I add more O2 molecules. So if I have 5 O2 molecules, that gives me 10 oxygens on my reactant side. That'll equal the 10 oxygens on my product side. Now at this point, everything seems to balance, and it doesn't hurt to go back through and just double check. Okay, but once we're done with this, what we're going to do is we're going to actually then fill in those stoichiometric coefficients. All right, well, I have 1 C3H8. Now, technically, I don't need to write a 1 there. I'm just doing that as a visual so you can see. Normally, I'd just leave it blank. That implies a 1. I have how many O2s? Well, I've got 1, 2, 3, 4, 5 O2s. So I'm going to get rid of those O2s and put my 5 in there. Remember that 5 represents 5 O2 molecules. Right? Don't forget, that's what those stoichiometric coefficients are representing. How many CO2s do I have? Well, I have 3. How many waters do I have? Well, I have 4. There you go. There's my balanced equation. My coefficients are 1, 5, 3, and 4. Those are the smallest whole number ratios too. If I divide by 2, I'm going to end up with fractions. I don't want fractions. Okay, so my equation is balanced. Right, let's go through another one. This one will deal with something that's got polyatomic ions in it. So once again, start from the left, move to the right. So starting from the left, I run into sodium. I've got 2 sodiums on my reactant side. I've got 3 sodiums on my product side. Want to balance out those sodiums. Well, how do I get 2 and 3 to be equal to each other? Well, I need more sodiums on my reactant side, so I need to add another Na2CO3. Remember, I can't just add sodium because that sodium's bonded to that CO3. So I have to add another Na2CO3. Well, now I've got 4 sodiums on my reactant side, 3 sodiums on my product side. So now I need more sodiums on my product side. I add an Na3PO4. Now I've got 6 sodiums on my product. Now I've got 4 sodiums on my reactant side, 6 sodiums on my product side. So I need 2 more sodiums. And sometimes it'll be back and forth like this. Okay, so just keep that in mind. Now I've got my sodiums balanced. Keep moving to the right. So I hit my carbon next. But now that's a polyatomic ion. So what I want to do is check, is there a polyatomic ion on the product side that's the same as the one on the reactant side? So I have CO3 on the reactant side. Is there any CO3 on the product side? No. There's a CO2, but that's not the same. So I'm going to have to balance the carbons and oxygens individually from this. So let's deal with the carbons. How many carbons do I have on the reactant side? I've got 3. How many on the product side? I've got 1. So I need 2 more carbons on the product side. Okay, now my carbons are balanced. Now I start moving to the right again from that carbon. I hit the oxygen. Remember, going to balance those last if possible. Go from the oxygens, I hit the hydrogens next. Going to balance those last if possible. Next thing I hit is the PO4. Well, I have PO4 on the reactant side, and I have PO4s on the product side. So I'm not going to break that up into phosphorus and oxygens. I'm going to balance it as just a PO4 itself. I'm going to keep those combined. It's going to make it easier. So I have 1 PO4 on the reactant side. I have 2 PO4s on the product side. In order to get those balanced, I need to add another PO4. So now everything but hydrogens and oxygen is balanced. So I can balance either oxygens or hydrogens at this point, whichever one you think is going to be easier. All right, so I'm just going to go back and walk through balancing the oxygens. I've already balanced out the oxygens and the PO4s. So I'm going to ignore those oxygens just to make my calculations a little bit simpler. All right, so really I'm going to worry about all the oxygens that aren't in those PO4s. So I've got 9 oxygens on the left-hand side. On the right-hand side, I've got 7 oxygens. Well, how can I get 9 equal to 7? Well, I need 2 more oxygens. Now, if I add another CO2, that'll give me 2 more oxygens, but that'll also change my number of carbons, which means I'm going to have to add more carbons on the reactant side, and then that's going to mess everything up. So instead of adding 1 more CO2, what I can do is I can add 2 more waters. Okay, so now the number of oxygens on the reactant side is equal to the number of oxygens on the product side. Now I can check my hydrogens. Well, I've got 6 hydrogens on my reactant side. I've got 6 hydrogens on my product side. So I don't have to worry about balancing out my hydrogens. They're already balanced. So now I just need to take these and write out the appropriate stoichiometric coefficient.
We have 3 sodium carbonates. We have 2 phosphoric acids. We have 2 sodium phosphates. We have 3 carbon dioxides. And we have 3 waters. And so we want to go back and double check to make sure that we've got equal number of the atoms on both sides of the equations. So you want to go back and count total numbers of those things as the last step.
All right, you remember when I was talking about number 5 on that hint list and it was kind of long and complicated? This is the example that's going to go through what I was talking about. Okay, and keep in mind, this is just to help make things easier when you're going to balance these equations. You don't have to follow those hints, but I think they're going to find that they're going to help you out. So, just like we started before, start from the left, work to the right, balance everything but hydrogens and oxygens first. Starting from the left, I have 4 carbons on the reactant side, 1 carbon on the product side, so I need 3 more carbons, which means I need 3 more CO2s. Carbons are balanced. Now I'm left with hydrogens and oxygens. Well, this is where I was saying if you have an element that's in more than one compound on both sides of the equation or either side of the equation, leave that alone. Balance that last. So oxygen is in every single one of these, so I'm going to focus on the hydrogen first because that's going to be easier to balance initially. All right, so I've got 5 hydrogens on the reactant side. I've got 2 hydrogens on the product side. So there's a difference of 3 hydrogens. Now I can't just add 3 hydrogens though, but if I add 2 water molecules, now I have 6 hydrogens on the product side, 5 on the reactant side. If I add another C4H5O, I've now got 10 hydrogens on the reactant side, got 6 hydrogens on the product side, so I need to add a couple more waters. So now I've got 10 hydrogens on the reactant side, 10 hydrogens on the product side. What's the problem though? Well, I added some more carbon. That was unavoidable So now I have to go back and rebalance out that carbon. So I now have 8 carbons on the reactant side, 4 carbons on the product side. I need to add 4 more CO2s. Now my carbons and my hydrogens are balanced. All I need to worry about is my oxygen. So let's look at totals here. On my reactant side, I have 4 oxygens total. On my product side, I have 21 oxygens total. So in order to get 4 equal to 21, technically I have to add 17 oxygens. That's going to get really complicated. I can't add any more C4H5O. If I do that, I'm going to have to change my CO2s and water again, which is going to increase the oxygen. This is going to be a mess. Now, what if I look at the fact that I have 21 oxygens on the product side? If I ignore the O2 for a second, I have 2 oxygens on the reactant side then. So 21 minus 2 leaves me with 19 oxygens that I need. Well, if I'm left with needing 19 oxygens, and those need to come from the O2 molecule, if I take the O2 molecule and multiply O2 by 19 halves, so 19 over 2 times 2 would be 19 oxygens. That's where I'm talking about using those fractions to help balance out these equations initially. So when I fill in the other stoichiometric coefficients, C4H5O, there's 2 of those. CO2, there's 8 of those. Water, there's 5 of those. So I have a balanced equation here. The problem with this, though, is I have a fraction for one of those coefficients. I can't have fractions. I need the smallest whole number ratio. So I need to get all of those fractions to whole numbers. Well, how do I do that? Well, how do I get 19 over 2 to a whole number? Well, if I multiply it by 2, that'll give me a 19, right? But I can't just multiply the 19 halves by 2. I have to multiply all those coefficients by 2. So for the C4H5O, if I multiply it by 2, it becomes 4. The O2 coefficient becomes 19. CO2 becomes 16. And the water becomes 10. That is the smallest whole number ratio. Now, you can get those numbers by just continuously adding more and changing them and going back and forth. It's just going to take you a longer time than using that fraction method. If you're confused about the fraction method, there's nothing that says you actually have to use it. All you need to be able to do is get the smallest whole number coefficients to balance these equations. Once we're done with all this, we should check our values. So I've got 16 carbons on my reactant side, 16 carbons on my product side. I've got 20 hydrogens on my reactant side, 20 hydrogens on my product side. I've got 4 times 1, that's 4, plus 19 times 2, that's 38. So I have 38 plus 4 is 42 oxygens on my reactant side. Product side, I have 16 times 2, which is 32, plus 10 times 1, so that's 42. So I have 42 oxygens on my product side. So that's how we're going to get these balanced equations. Now, those balanced equations are going to show how we count these atoms and how we show these atoms in a chemical reaction. But how are we going to actually use these chemical equations with something we can measure out in the lab? Because we're not measuring atoms in the lab. So what do we do to relate that atomic level to the macroscopic level? Brings up our buddy, the mole. Remember, not the animal. It's a conversion factor dealing with Avogadro's number. Okay, don't forget about that. That's important. The other thing we need to remember is molar mass. Remember, that's the mass in grams of 1 mole of a substance. So if we look at this chemical equation again, now I can relate those coefficients to moles of the compounds instead of just atoms and molecules. Right? So if I look at the C7H8, how many moles do I have in this reaction? So if I look at all of those coefficients now tell me how many moles of each one of these compounds I have in that reaction. So now for the C7H8, well, if I have 1 mole of C7H8, that means I have 7 moles of carbon atoms. Now those are moles of carbon atoms. That's not number of carbon atoms. If I wanted the number of carbon atoms, I'd take that 7 times Avogadro's number to give me the number of carbon atoms for that reaction. Okay, so these are all moles. Right? How many oxygen moles do I have? None from that. I've got 8 hydrogens. For O2, I've got no carbons. I've got 18 oxygens, no hydrogens. For the CO2, I've got 7 carbons, 14 oxygens, no hydrogens for the H2O. Got 0 carbons, 4 oxygens, 8 hydrogens. Those are all the same numbers as when we were talking about the molecules. Okay, so those stoichiometric coefficients relate to molecules of things, atoms of things, as well as moles. All right, we're going to be using those with mole units a lot more now than the molecules and atoms. All right, so let's look at how we can use this information. Well, if I look at this reaction, and if I have 1 mole of C7H8 react completely, how many moles of product are going to be formed? Well, I can do a conversion with something called a mole-to-mole ratio that's going to come from the balanced equation. And we've done mole-to-mole ratios before with balanced formulas. Now we're going to deal with balanced equations. So if I start with 1 mole of C7H8, well, my conversion factor then is going to be related to those coefficients out in front of those molecules. Remember, I want to find out how much of each product is formed. So my first one is CO2. So my ratio there would be 7 moles of CO2 to 1 mole of the C7H8 based upon that balanced equation. So when I multiply that out, I end up with 7 moles of CO2. Do the same thing with the water. Except now the ratio is going to be a 4-to-1 ratio, 4 moles of water to 1 mole of the C7H8. So I'd end up producing 4 moles of water. So these coefficients just now become more conversion factors. But it's going to be important conversion factors. It's going to help us relate all these compounds to each other in a balanced chemical equation. So it allows us to predict how much products are going to be formed, how much reactant is going to be consumed, lots of different things. Okay, but it's going to be focused around this mole-to-mole ratio that comes from these coefficients. So if I have 5 moles of C7H8, how much of each product is formed? Well, I just multiply it by that same ratio, so now I end up with 35 moles of CO2, 20 moles of H2O. Right? It's that conversion factor. Something that's not easy to do in your head. Start with 7.64 moles of C7H8. Same setup, I've just changed that value. And it's the same setup for both of those because it's the same chemical reaction. Right? I can look at the other reactant. So if 7.64 moles of O2 completely reacts, how many moles of each product are formed? Well, I start with my 7.64 moles of O2. Now moles of O2 on the bottom, moles of CO2 on top. I have to use the coefficients in front of each one of those. So now it's 7 moles of CO2 to 9 moles of O2. That ratio has changed because I've changed from using the C7H8 to using the O2. But that mole-to-mole ratio is still coming from that balanced equation. When I look at the water, it's 4 moles of water to 9 moles of O2. All right. I can even relate the reactants to each other. I can relate the products to each other. I can convert between any of these things. Okay, so let's say I have 7.64 moles of O2, and I want to know how many moles of C7H8 it's going to react with. I can set up that conversion. So 7.64 moles of O2, from the stoichiometric coefficients in the balanced equation, I get 1 mole of C7H8 is equal to 9 moles of O2. Calculate out that I get 0.849 moles of C7H8. I can also go from products to reactants. So if I want to form 6.35 moles of CO2, I can calculate how many moles of each reactant I'm going to need to produce that much product. Still that mole-to-mole ratio. So 6.35 moles of CO2, set up the 1 mole of C7H8 to 7 moles of CO2, get my moles there, do the same thing with the oxygen. Now if you notice, in all instances, the number of sig figs I'm writing out is not dependent upon that mole-to-mole ratio. You've got to look at that mole-to-mole ratio. Those are going to be exact numbers. You don't use those to help determine how many significant figures your final answer has. It's similar to dealing with prefix conversions. You don't use those in determining sig figs. Okay, so don't use those mole-to-mole conversions. Otherwise, every time you do this calculation, you'd end up with one significant figure. So keep that in mind when you're doing those calculations. Mole-to-mole conversions aren't included to determine sig figs. All right, so that's the initial start to doing calculations with these chemical equations. We're going to be doing a lot more with this, so you need to get this balancing chemical equations down. You need to understand these mole-to-mole conversions that come from these stoichiometric coefficients. We're going to be doing a lot more of this. So make sure you practice that and make sure you get it down solid. And that's going to be it for our chemical equations then.